Alright, we're going to find the surface area of rotations, and this is not a huge leap from where we've been in the past. Let's see here. So the idea here is that we've already talked about how to find the arc length of a curve. We looked at several little hypotenuses added together. So that gives us a length of the line, and then if we wanted to rotate that around an axis, or any line, then basically we're going to turn those little things into circles. So empty circles, not disk, but kind of like somewhere between the shell and the disk method. There'll be just like hula hoops, empty circles. And that creates a solid shell on the outside, just one shell, not shells stacked inside of each other, but a solid shell that we could find the surface area for. So the formula looks like a combination of, right here, 2 pi r, where we have 2 pi f of x for around the x-axis. That's the circumference. And then the circumference of what? That curve, which was the square root of 1 plus f prime squared. Okay? So it's a combination of the arc length and the circumference formula. So if we're going to go around the x-axis, we're going to write everything in terms of x. If we're going to go around the y-axis, we'll write everything in terms of y. So the y formula is 2 pi, the integration from a to b, of g of y times the square root of 1 plus g prime squared. Okay, integrate in terms of y. So let's do a couple of examples here. We're going to find the surface area of y equals the square root of x plus 1 from 1 to 5, and we're going to rotate that around the x-axis. Now let's try and draw this out. Hold on. Okay, I'm back. So let me just draw this out so you'll see it. Okay, I'm not a good drawer, but we can put the graph of this square root of x plus 1 down. So we know this is a square root function, and we know because under the square root is x plus 1, that means it's shifted over to the left one. You may remember that from pre-calculus. So the graph looks something like this of the function, but we're going to run it from 1 to 5. Okay, so we're going to pick out a piece here from 1 to 5, and we're going to highlight that little region, and we're going to wrap it around the x-axis so that we have something similar down at the bottom. So we'll have this hollow shell on both ends. Okay, so let's write all this out. So what do we need here? We need lots of room, kind of. But we know that the original function f of x is the square root of x plus 1. Okay, and we know that we can write that a little bit better as x plus 1 to the 1/2, because now we need to take the derivative of it. So derivative of that, we'll use the chain rule, 1/2 times x plus 1 to the negative 1/2, and then we're going to square that. And that will give me 1/4, and that'll be x plus 1 to the negative 1. So I'm just going to put it on the bottom as x plus 1, since it'll be to the negative 1. But that gets rid of the root. Now we've got all the pieces, so let's start dropping them into our integration formula here. So it'll be 2 pi. In terms of x, it'll be from 1 to 5. And the function was f of x, which was the square root of x plus 1. So let's just write that as x plus 1 to the 1/2. And then we'll have the square root of 1 plus 1 over 4 times x plus 1. All that is dx. So now we got to kind of figure out what in the world to do here. So we've got this whole number and fraction underneath the square root. So let's try and make that one big fraction under there. That may not be your first thought, but we'll keep the 2 pi from 1 to 5, and we'll keep the x plus 1 to the 1/2. But under the square root, let's turn these into like denominators. So we'll turn the 1 into 4 times x plus 1, which I guess I might as well just go, well, I'll leave it like that, over 4 times x plus 1. I have reasons for leaving certain things the way it is. And that would be plus what's already there, 1 over 4 times x plus 1. And that's a dx. Okay. We're just going to need some room for this problem. So I'm going to rewrite it again. It's 2 pi from 1 to 5 of x plus 1 to the 1/2. I'm going to have the square root here. And now I've got a common denominator, so on the bottom it'll be 4 times x plus 1. That's the common denominator. Now up top I'll have 4x plus 4 plus 1. So it'll be 4x plus 5. So that may seem a little worrisome, but let's see what happens as we try to continue this thing. Okay, so I can push some things in, I can pull some things out. It's just really how am I going to manage it. So let's see here. I can pull this down here. This x plus 1 is in the denominator of a square root, right? So let's kind of say I imagine reworking this whole thing. I have the x plus 1 to the 1/2 out front. Let's kind of color code things so you can see them. That was out here. It's still out here. I'm going to write the numerator as 4x plus 5 to the 1/2. So let's make that green. And then there's going to be a denominator of 2, because that's the square root of 4, x plus 1 to the 1/2. So that's the yellow part down here. So if I look at that and I kind of picture everything that I have there, and let's throw a dx over here. Let's make my integration thing look a little bit bigger here, since I've rewritten things really large. But at this point, what we see is we can cross out this x plus 1 square root in top and bottom. And I can even pull that 2 out front that I have here. So I'm going to take that 2 that's in front of the integral and the 2 that's in the denominator of this integral and pull it out. Okay. So in that, I'll have pi integral from 1 to 5, and what I'll be left with inside is the square root of 4x plus 5 to the 1/2 dx. So that is pretty simple to work with. It is a u substitution, so just to make sure we don't make any mistakes, let's go ahead and do the u substitution. So we'll let u equal 4x plus 5. du will be 4 dx. So 1/4 du will equal dx. So let's rewrite this thing. So we'll have pi out front, and we will put 1/4 du in place of dx, and then in place of 4x plus 5 we'll have u, which will be to the 1/2. So I'm going to integrate 1/4 u to the 1/2. Okay. So when I do that, I get pi still out front, u goes up to exponent of 3/2. If I flip the 3/2, that'll be 2 over 12, so 1/6. I believe, let's backtrack here. If we pull the 3/2 out front, we will have 1/4, yes, because it'll be 3/12, yes. Okay, so now we're going to go back to x. So we'll have pi times 1/6. Excuse me, I don't need the parentheses the way I put it. Pi times 1/6 times 4x plus 5 to the 3/2. And that's going to be evaluated from 1 to 5. So hopefully we're going to fit this in somewhere. I didn't realize it was at the bottom of a page, but these things get rather large. So let's see here. I'm going to make one thing look a little bit better before I continue. So let's let x equal 5. So in that case, we'll have pi 1/6. 4 times 5 is 20. This is 25. 25 square root of that is 5, and then raise it to the third. That's 125. And then we'll minus, let x equal 1. And that'll be pi 1/6, 1/6 pi over 6. And if I plug 1 in, that'll be 9 to the 3/2, so that's 3, that's 27, I believe. So let's see what we've got here. We've got 125 minus 27, so that's 98 times 1/6 times pi. So 98 divided by 6, is that anything? Not a nice number. We know they're both divisible by 2, so that would be 49 pi over 3 if this works out to our advantage. Alright, so that is a surface area. That is surface area. So that's in square units if you want to make that leap. Alright, one good example though.